This video is going to be about acids, bases and the value of Kw. Now, all the topics around acid and bases will be split into two videos. The first one will be acids, bases and Kw, look at what an acid and a base is, strong versus weak acids, conjugate pairs, the oxonium or hydronium ion, Kw and some examples throughout. The next video will be all about pH, Ka and pKa. We'll talk about the pH scale, what Ka is, what pKa is, and some of the calculations and examples throughout of that. So let's start with the definitions of an acid and a base. Well, there are several different definitions out there depending which ones you're looking at. So here we are talking about a Bronsted-Lowry acid. There's a different definition for a Lewis acid and a Lewis base and things like that. But at A level you'll mainly focus on this. So a Bronsted-Lowry acid is considered a proton donator, so a species that can donate a proton. Whereas a Bronsted-Lowry base, it's a proton acceptor, so it's a species that can accept a proton. And we'll look at some examples throughout. So let's look at strong acids. Well, strong acids can completely dissociate in solution. So if you have hydrochloric acid and you add that into water, then it will completely dissociate into its ions, H plus and Cl minus. And that's 100% come apart. The structures come apart completely, not partially or there's an equilibrium, it's completely come apart. However, there's one thing we must actually note when we're talking about this. You may know from GCSE or other equivalent levels that we usually use H plus to represent a proton. Well, in a matter of fact, H plus is not H plus, it's actually H3O plus. And that's known as the oxonium or hydronium ion. So basically what happens is you have the acid, HCl, you add that to water as we're putting it into a solution. They react together to form the hydronium ion, H3O+, and a chloride ion. And that's actually what happens. So a proton isn't just H+, it's an H+ that's been attached to H2O, giving it a positive charge, and the proton can then come off this H3O molecule and attack something else. So that's one key thing you need to note when you're doing A-level chemistry or equivalent, is that the true reaction is that. You'll sometimes see it written as H3O+, you'll sometimes see it written as H+. It doesn't really matter which way you use it. H+ is commonly used because it's just easier to write than H3O+ every single time. So that's strong acids. Let's look at weak acids. So weak acids are, they only partially dissociate when put in solution. So we look at ethanoic acid, for example. So CH3 COOH is ethanoic acid. Now, this will partially dissociate into the H plus and the CH3 COO minus ions. Again, I've omitted water just to make it quicker and clearer, as this is what's commonly used, just H plus. And this equilibrium basically shows that it only partially dissociates, because we can change the conditions to have more or less protons. If you remember my videos all about K and equilibria and things like that. So for example, I don't know the exact value on this, but it could be, if we put, say, 1 mole in there, 90% of it will be the acid and then 10% of it will be the dissociated ions. Is just a quick example of what could happen, just to show that it doesn't fully dissociate, unlike strong acids. So that's just the difference between weak and strong acids. Now let's look at bases. Well, a base is a proton acceptor. Now it's basically any species that, like I said, can accept a proton. And the common ones you'll come across are OH- and NH3. So OH- is an oxygen and a hydrogen, and it has a minus charge, and it has the lone pair where usually you would have the other sort of hydrogen coming up from water, so that can accept a proton where that other hydrogen would be. And one common reagent to get that is sodium hydroxide. We put that into water and that will break up into the hydroxide anion and the sodium cation. That's how we get OH. So what basically happens is you get OH- plus an acid that has some sort of proton, and it forms to form H2O. And as you can see, the OH minus has accepted a proton, therefore it is a base, or an alkali. Another example, using nitrogen, is because nitrogen is NH3, and it has a lone pair on that nitrogen that can accept a proton. So you'll have reactions similar to this. You have NH3 plus H2O, go to NH4 plus and OH minus. As you can see, it's acted as a base as it's accepted a proton off the water molecule. However, you can also see that it's created a different base in the process. And this will take us on to conjugate pairs. Next. So conjugate pairs. Well, this is a pairing of an acid and a base in reaction. So I'm just going to use an example to demonstrate this, as it's easier to understand with examples. So you have HCl, so H2O, could react to form H3O plus Cl minus. What we notice here is this is an acid. As it's donating a proton, we can see that it goes to Cl minus, and this is acting as a base. It's accepting a proton going from H2O to H3O plus. So what we can say is this is an acid, this is a base. But as this is an equilibrium, and you'll see if we take the reverse reaction, we can see that, okay, H3O plus goes to H2O, so that's also acting as an acid in the opposite direction in the reverse reaction, and this is acting as a base as Cl minus is accepting a proton to become HCl again. And what we can actually do is we can pair these up as an acid and a base pair. Well, if we call this acid 1, for example, then we can say this is base 1, because this acid has formed this base. Therefore, they're kind of a pair. Hence, they're a conjugate pair. And we can say this is acid 2, and it's forming base 2. So this is a conjugate pair. And that's basically what conjugate pairs are. You're just saying the acid and the base that match up. So HCl is being an acid to form Cl minus, while Cl minus is a base that forms the acid in the reverse reaction. And the same applies to H2O and H3O plus. And that's just the simplistic way of going about conjugate pairs. Now let's move on to pure water. Well, interestingly, pure water conducts electricity, and you may think, oh, that's obvious. Water conducts electricity all the time. Well, don't forget tap water and things like that contain a lot of minerals and a lot of ions and things like that which can carry the charge. So you may have calcium or potassium ions in there, and they can move when you run a voltage through them. And that's what conducts water. But water, you think, is just H2O. Well, there's no ions in H2O, are there? So how come that can conduct water? Well, the reason for that is water can react with itself to form ions. So you have two water molecules can react with themselves in an equilibrium to have H3O plus and OH minus. And another way of writing this, you could just say H2O is in equilibrium with H plus and OH minus. Obviously depends if you would like to use the H3O or the H plus terminology here. But like I said, water reacts with itself to create these ions, and when you run a voltage through this, the ions can move to the electrodes and donate or accept electrons and pass it through the water. And that's why pure water can actually conduct electricity. Now let's look at Kw, which is the ionic product of water. Well, going back to the previous slide where I said H2O is in equilibrium with H plus and OH minus, well, we can actually predict where the equilibrium is going to lie. And if you remember from my video on equilibria, Kc, which is the equilibrium constant, concentration of products, over the concentration of reactants, which in this case is the same as H plus and OH minus concentrations over the concentration of H2O. Now, what I'm about to say is very, very important. H2O is in excess. Now, what this means is we can get rid of it from the Kc value, because if it's in excess, changing the concentration of H2O is not really going to affect the equilibrium at all, and it's just kind of an assumption that scientists make to make the mathematics a bit more simple. So what this goes, it goes from Kc to Kw, and it just simply equals H plus OH minus. Because we've eliminated this value of water at the bottom, because there's just so much of it, it would be like saying, oh, 1 over infinity, as it's just so large, and infinity minus 1 or something like that, which is just still a very large number, and we just wouldn't really get an answer out of this. So that could be omitted, and that's Kw, the ionic product of water. Now at 298 Kelvin, Kw equals 1.00 times 10 to the minus 14, and units are very important, moles squared dm to the minus 6. And that is a value that you'll need to know. You may get given it depending on your exam board or not, but it's very handy because what we can do is we can actually work out the number of protons or the number of OH minus ions, particularly OH minus ions, because we can use the pH scale, which I'll discuss in the next video, where we can figure out the number of protons depending on the pH. We now know the value at 298 of Kw, so therefore we can work out the number of hydroxide ions in a solution. And this is good if we need to know that value for something. If we look at an example of Kw, if the concentration of H plus ions is 1 times 10 to the minus 8 moles per dm cubed, what is the concentration of hydroxide ions at 298 Kelvin? Well, Kw equals H plus OH minus concentrations. We'll rearrange that as we want to find OH minus, so concentration of OH minus equals Kw over concentration of protons. From the previous slide, we know Kw is 1.00 times 10 to the minus 14, and concentration H plus is given in the question here, so now that's 1 times 10 to the minus 8, which gives us a value of 1.00 times 10 to the minus 6. Now we also want to look at units, don't we? So Kw has the units of mole squared, dm to the minus 6, and the units of concentration is moles per dm cubed. Now moles and one lot of moles there cancel out, dm to the minus 3 and minus 3 would cancel out, so it would just be minus 3 there, meaning the units are moles per dm cubed, which makes sense because we're looking at the concentration of hydroxide ions. Concentration is always in moles per dm cubed. And that's just a simple example of the ionic product of water. Now that concludes this video. If you found the video helpful, please share it with your friends and hopefully we can help them as well. Subscribe for more videos and like this. Thank you very much. Enjoy your day.